Okay, so now we'll start the subject of. So the first four chapters were thermodynamics, and now we'll start the chapter subject of electrostatics. Okay, we'll study electric charges, and electrostatics means we'll study properties of charges that are at rest. Okay, and then in later chapters we'll study charges moving. Okay, so the next four chapters we'll study charges, but they'll be at rest. Okay, so that's the properties we'll study. So you guys know that you encounter two kinds of charges, and you can call them two different names. We call them positive and negative charges. You could call them A and B, whatever you want to call. Okay. And you also probably know that like charges repel each other, and unlike charges attract each other. And so one of the first things we want to know is, okay, the direction of the force is always directly opposite. So you can connect a line to these two charges, and the direction of the force is along that line. And then what is the next thing you want to know? The magnitude of the force. Okay? And Mr. Coulomb gave us the formula for the magnitude. Okay? It's a constant, so we use the same letter K that we use. So to distinguish it from Boltzmann's constant, we give it a subscript. It's the Coulomb's constant. Okay? Times the product of their charges and divided by the distance squared. Okay. And this is Coulomb's formula. All right, so that's the magnitude and direction of the charges. Okay, so that's one of the main results. Okay. All right, we might as well talk about this as well. So what do these two charges do?
Repel.
They repel each other. Okay. And the magnitude of the force depends on the distance. Okay. But let's say this charge is here and this guy is in New York. Does he still repel him?
Technically, but not practically.
Yes, so he repels him. Okay. The force just gets smaller. How about if he's in the next galaxy? He'd still repel him. Okay. Now let's do the following. I'll take this charge and I'll jiggle him. Okay. When does this guy know about it?
Speed of light.
Yeah. So, if you make any changes, if you jiggle them, that information travels to him at the speed of light. Okay. So the further out he is, the later he gets to know about it. Okay. So the question becomes, if he's in New York, how does this guy push him? If this guy's here and that guy's in the next galaxy, how does he push him?
Bring them closer together.
No. Can I push you from here? No.
Electromagnetic force.
Okay. So how do you answer that question? Yes. So to answer questions like that, what we did was we invented the concept of electric fields. Electric fields are denoted by E. They are a vector field. What does that mean? Yep.
They're in like each direction.
At every point, we associate a vector. Like a wheat field, at every point on the field, there's a wheat plant. Okay, so this is a vector field. And you can see that the vector field associated with this guy is radially pointing outwards, and as you go further out, the magnitude of the vector is decreasing. So you can think of a point and a hedgehog. Yeah. You like hedgehogs? All right. All right. So the question is, how does this guy push him? Here's the story. All this guy does is he creates electric fields all around him. And this guy is just feeling the electric field right where he is. He doesn't know who created this electric field. He doesn't care who created this electric field. All he's doing is responding to this electric field. Okay? So, when you jiggle him, what happened?
Create vectors of different.
When you jiggled him, this electric field changed. And the change in the electric field traveled at the speed of light. Okay, so that's the simplified picture. And that's the story.
Is the electric field like a device we use to understand, or is that actually the physical mechanism?
So that's sort of a device we use to understand. When you use quantum mechanics and stuff like that, quantum electrodynamics, you're emitting virtual photons, and that's what conveys the force. Okay. Yep. Well, yep.
Is this different from electromagnetic radiation, or is it the same?
Electromagnetic radiation has both electric and magnetic fields in it. It is related. Yep.
So what you're showing us is just electric?
Yeah, just electric. So, you'll have to wait 4 more chapters. When you get the charges to move, then they produce both electric and magnetic fields. Yeah. So when a charge is at rest, it's only producing an electric field. And when it moves, it's producing both an electric and a magnetic field. So you want to hear something more freaky? Huh? What?
What did you say?
Freaky. So I just told you that a stationary charge, what does it do? Produces electric field. If you get it moving, then it'll produce both electric and magnetic fields. I'm not drawing what the direction of the field is. All right. So here's a charge. Here you are standing. What do you see?
Electric field.
Yeah, it's producing an electric field. See, this guy goes to college. He knows the answers. Here's your buddy. He's running towards the charge. What does he see?
That doesn't make sense.
I told you it was freaky.
Does he see nothing? Because you're in the toilet?
Wait. So
Think about it.
I'm thinking. What's your question?
it's magnetic for the dude moving, but not the dude standing still.
Oh, I see what you're saying.
So the dude moving sees both an electric and a magnetic field.
So if you threw a magnet at, or not throw it, if you put a magnet there, would it be attracted to the
Yeah, it would be different if you throw a magnet.
Not throw it, but like, let's see. I'll ask you later.
Mhm. So did you guys understand that? So it's relative motion. Some journeys are taken with the mind. And those are the most exciting journeys. All right? So, we are studying electrostatics. Okay, we are studying about electric charges and they're at rest. Okay? All right, so I'm going to go. Did you guys understand the 2 main points of this chapter? Okay. Go ahead.
Oh shit. You can't just call me out.
No, I didn't call you. Yeah.
Yeah.
Oh, God.
Yeah.
Electric charges and.
No. Well, you look like you had a question.
Oh,
If
no,
you don't,
I'm
then
good.
okay, then
Just
you're
one
good.
topic.
Then you're good. All right. So, do you know how many electrons this table has? And how many electrons do you think that table has? How many gas molecules are in this room? Anybody remember?
2 to the 4.
Huh?
10 with 28.
10 to the 28. 10 to the fourth moles.
Okay, same.
No, not same thing. 10 to the 28 molecules. That's how many electrons there are on this table. Let me ask you, how many protons are there?
10 to the 28.
Exactly the same. How many electrons are there in this building? About 10 to the 32. How many protons? Exactly the same. Okay? So, why is it that? I mean, all objects that you see are neutral. That's because if you separate a positive charge and a negative charge, the force of attraction is so strong that they'll neutralize each other. It's hard to separate charges. You separate a bunch of charges, and what happens? You see lightning. Lightning is neutralizing the charges. Okay? Violently. Okay. All right, we won't separate that many charges. So let's say you want to separate a little charge, you can do the following. You can take these materials and rub it against these materials. So what this shows you is these materials, atoms in this material like to give up electrons. They're not holding on to them as strongly. These guys like electrons. And you encounter this in a very common substance, H2O. O is greedy for electrons. This Mickey Mouse molecule, the hydrogen atoms will give up their electrons. Okay? So the center of the negative charge is here, and the center of positive charge of this molecule is over here. Okay? All right, so anyway, if you take these materials and rub against these guys will give up electrons, and these guys will attract electrons. So these guys will become negatively charged, and these guys will become positively charged. So this is called triboelectricity. You can charge two objects via friction. And you've all experienced this when you walk in the winter on a carpeted floor, you get charged. Do you not get charged in the summer? Huh?
Is it too humid?
Yes, so the humidity takes away your charge, that leaks away. Okay, so in the winter, yeah. All right. So let me show this to you. There you go. All right, so you see, what? Yeah, of course it's cool. Better than YouTube. Better than YouTube. All right, so see, this is neutral, this is neutral. This is rubber against wool, and wool gives up, so that's how you can charge them. And you guys see the two, the negative is repelled to the negative. There you go. All right. So you have two kinds of charges. Like charges repel each other, unlike charges attract each other, and the magnitude of the force is given by Coulomb's law. Okay. Okay, what are insulators and conductors?
Insulators
Did you just read there?
No, it came from over here.
So we are talking about electrical insulators and conductors. Okay, so if we have time, I'll give you the more detailed picture, but for now, I'll give you a simplified picture. So here's a model of, let's say, wood. And here are all the atoms. And all these atoms are neutral, and they're holding on to their electrons tightly. So everything is neutral, and there's no free charges. You connect a battery to this thing, and no current will pass through it. Now, if this were a piece of metal, what happens is, if you arrange atoms in a metal like that, in a crystal, they can achieve a lower energy state by giving up a couple of their electrons. That depends on the metal. They're a couple of their outermost electrons. And these guys, these electrons, you can loosely think of them as they're moving about like the gas in this room. Again, just you'll have to get a more refined picture later, and we'll give you that later. All right, so these guys are fixed, the positive ions, and these negative ions can move about freely. Now, when you connect a battery like this, what the battery will do is it'll establish an electric field like that in this metal. And you'll learn that, well, can these positive guys move in a metal? No, they're fixed. These negative guys can move, and they move in a direction opposite to the electric field. Okay, so when you connect a battery, these charges will move, and that's an electric current. And and we'll study about that later. Yep.
Why does the metal heat up in a situation like
Okay, so these electrons, they're moving in response to the electric field. Electrons are very light, and they pick up speed pretty fast. And then they'll collide onto this guy, lose their energy. And that energy gets transferred to heat. Okay, so electrical energy got transferred to heat. In a bulb, it got converted to light, and so on. In a washing machine, it got converted to the motion. In an electric motor, it gets converted to mechanical energy. So insulators are things that do not have the free electrons. Conductors have free electrons. And semiconductors are materials that have in-between electrical properties. Okay? In addition, you can change the number of free electrons in semiconductors, depending on what kind of semiconductor you have, by adding impurities to the material and so on. Okay? We won't worry about that. Okay, so now we'll talk about Coulomb's law. What is this about? This guy, Mr. Coulomb, gave you the magnitude of the force. You know the direction of the force. What is the direction of the force? It's along the line connecting the two charges. Okay? For repulsive force, it's away, and for attractive force, it's like that. Okay. So the magnitude of the force is the Coulomb's constant times the product of the charges divided by the distance squared. So if you take these two charges and double the distance between them, the magnitude of the force becomes 1/4 as great. Yeah. The electrostatic force is large because this Coulomb's constant is large. Yeah. By the way, if you guys remember from Physics 1, this formula is very similar to the gravitational force. Yeah. It's just that this gravitational constant is very small, and so the gravitational force is very weak. Okay? But the Coulomb force is large. Okay? This sort of illustrates how large the force is. So here's a hydrogen atom. Okay? This is a positive charge, negative charge, so there's a attractive electrostatic force. Is there any other force acting on the hydrogen, in the hydrogen atom?
The strong force? Is it the nuclear?
Okay, well,
There's one.
so here, the gravitational force also acts. This has a mass, that has a mass. So there is a gravitational force as well. Okay. Now let's compare these two guys. Okay. The electrostatic force between the proton and the electron, and the gravitational force between this guy and that guy. Here's the electrostatic force. This is in the hydrogen atom. These are actual numbers. This is the gravitational force. You take the ratio of the two. The electrostatic force is 10 to the 39 times larger than that. So let me say that in words. A trillion is 10 to the 12. That's 1,000 trillion times stronger. When this guy talks, you don't listen to him. Okay, so when you're considering the hydrogen atom, all you do is you have to worry about the electrostatic force. Nobody even mentions this. Yeah. So did you guys understand that? All right, so now here's an impossible task. Here's another amazing number. So here's roughly a liter of water, and here's a kg. Okay. Now let's say you took this and stripped this all of its electrons, roughly speaking. Okay. You couldn't do that. But let's say you strip this all of its electron. You strip this guy all of its electron. They would both be positive charges, and you keep them 1 meter apart. The repulsive force between them would be as great as the weight of the Earth. And that's what this says. As a second example, if you take two 1 kg blobs of protons and set them 1 meter apart, here's 1 meter, the force between them would equal the weight of the Earth. Yeah. So in general, I mean, in our everyday life, electrostatic forces are large, and so that's why if anything gets charged, it gets neutralized fairly quickly. Yeah. Here is a superposition principle. So let's say if you have multiple charges, so for instance, if you wanted to calculate the force on this guy, the superposition principle states the following. To calculate the force on this guy, just consider this pair, figure out that force. So the force between them is not being influenced by the presence of others. Yeah. So for instance, conversation between you is influenced by my presence. As soon as I walk out, the conversation will be different, right? Unlike that. Especially for Alicia.
It's because when he's not here, he's my press on.
I'm just kidding, all right? All right, so you see the repulsion between them. There you calculate this force. Then the force between them, you calculate ignoring this. And the net force on them is just the vector sum of these two forces. And you can do this, it doesn't matter how many charges you have, okay, so, to a certain extent. All right, that's the superposition principle. So here there's multiple charges, and so you can do the same thing with multiple charges. You want to calculate the force on this guy, calculate the force between these guys, these two guys, and all that, and then add up all the vectors. Okay. Okay, so it turns out that in nature there's only 4 forces. And this is rather interesting. Okay, so there's the strong force, the electroweak force, which consists of the weak and the electromagnetic force, and the gravitational force. These are the relative strengths. If the strength of the strong force is 1 unit, the electromagnetic force is 100 times weaker. Okay. And now, given this fact, you can immediately understand the following fact. So let's build a carbon atom. Okay. That's in your body. Plenty of those in your body. What is the carbon? So here's C. This is carbon 12. What do these numbers mean?
The atomic number and the atomic mass.
Yeah, so this tells you it has 6 protons, and this tells you how many protons and neutrons it has. And then, since the carbon atom is neutral, it must have 6 electrons. Do you guys know the size of this atom? (10⁻⁻10 meters. You know the size of the nucleus? 10⁻⁻15 meters. Okay. Now, here's a good picture to remember. If this were the size of a football stadium, the nucleus would be the size of a marble in the middle. So an atom is all mostly empty space. So you're all mostly empty space. So why can't you see through your hand? Those electrons scatter light. Okay. So if it was transparent, then you could see through your hands. Yeah. Now, why do I tell this story? Okay, this was all to set up the following. What do 2 protons do? They repel each other. Okay, why aren't protons popping out of your body?
Strong force.
Yeah. So like our friend says here, there's a repulsive force, and the reason that if they're not popping out, there must be a stronger force holding them together. And the strong force that's holding them together is 100 times stronger. Now here's the next deal. Okay, so this gives you the range of the forces, and you see the strong forces, the range is 10⁻⁻15 meters. What does that mean? So if you have 2 protons, and if they're further than 10⁻⁻15 meters apart, then the strong force goes to 0. It only acts on that range. Okay, so now you understand why the nucleus, all nuclei are that size, because all those particles have to be that close to be held together. If this proton was here, then he would be popping up. Okay. All right, so this gives you the range of these forces. Okay. So the electromagnetic force is 100 times weaker, weak force is 1,000,000 times weaker, and the gravitational force is very, very weak compared to that. The range is infinite for the electromagnetic and gravitational force. For the strong force, it's 10⁻⁻15 meters. For the weak force, it's even smaller, the range. Okay. And a lot of radioactive decay is the weak force is responsible for that. Okay. In quantum mechanics, they tell you forces are mediated by these particles by bosons, Strong force is mediated by gluons, electromagnetic force by photons, the weak force by W and Z bosons. And this is not detected yet, but postulated. So I'll tell you about this picture for 30 seconds. This is a very interesting picture. Okay, so here's the Big Bang. Okay. So we told you that there are four forces. Okay. At these energies, at the Big Bang, when the average energy of every particle was greater than that, at those energies, all those forces act as one force. Okay. We don't have a description of that yet, but that's what we believe. And as the universe cooled down, when the energies involved are that much, they separated into two forces. Gravity separated. We know gravity now. And this is called, this is grand unified theory, but we don't have a description of that either. We don't have a description of this, you don't have a description of this. Okay? So there are 2 Nobel Prizes waiting to be taken. For energies less than that, the electromagnetic and weak forces were acting as one, and here was the strong force. So the electroweak force and the strong force separated. We have a theory for both of these guys. So those Nobel Prizes are taken. As energy decreased, the electromagnetic force and weak force separated. Okay? At these low energies, that single force is appearing as 4 different forces. Yeah. So that's the story. Yeah. Yeah.
Is the giga electron volt, is that like the average energy per particle?
That's, yeah, you can think of it that way. That's the temperature of the universe, and if the temperature of the universe is, remember, the temperature is related to 3/2 kT. This is the simplified formula. Okay. So temperature tells you what's the average energy per particle. All right, so the important message was at high energies, the 4 forces we see is at low energies. As the energy changes, as energies increase, those forces might appear as 3 forces, at 2 forces, or 1 force at the very top, at the highest energies. Okay. All right. Now, there's many amazing facts. Here's an electron, and here's a proton. Okay. What are their charges? Positive and negative, and they're exactly equal to each other. Look at this guy. The proton is about 2,000 times heavier than the electron. And the proton is made out of 3 quarks. The electron is a fundamental particle. It's a point particle, sort of. Not a point particle, but very different natures. But their charges are exactly equal to each other, to as many decimal places as you want. Amazing. Okay. Okay, so Mr. Millikan won a Nobel Prize about 100 years ago, 120 years ago. What he found was, so he squirted oil drops, and then he would charge the oil drops, and I'll tell you in a second how. Okay. And he measured the charge on the oil drops. He did hundreds of thousands of these experiments. And what he found was every time he measured the charge of the electron, it was always an integer number times a smallest charge, a minimum charge. This is the charge of the electron. Now we know. But we didn't know this before Mr. Millikan. Okay. So you can go to Walmart and you can buy 1 electron charge, you can buy 2 electron charge, you can buy 10 electron charges. You can not buy half an electron charge. Okay. So this is quantization of charge. Any charge is an integer multiple of the fundamental charge. Now it turns out that quarks have fractional charges, 1/3 and 2/3 e, but we've never seen a free quark. Okay. If you want to see a free quark, you'd have to go back in time to this, about 10 to the minus 50 seconds after the Big Bang. So then you could see a free quark, but given that we're not there yet, you'll never see a free quark. Well, okay. All right, so I'll briefly tell you what Mr. Milken did to make this discovery. What is this discovery? That charge is quantized. It's an integer multiple times the smallest charge. Okay. So he would score the oil again, and he'd make these oil drops fall, and so these oil drops as they fall. Okay, what happens to hailstone? What happens to raindrops?
Freeze.
They reach terminal velocity. If the raindrops didn't reach terminal velocity, they'd be going too fast. You couldn't walk in the rain. Why do they reach terminal velocity?
Drag.
The drag force. Okay, so if something is falling and it reaches terminal velocity, what that means is their weight is equal to the drag force. Okay. So just like that, you scored a bunch of oil. These oil drops will reach terminal velocity. And you can, so the drops are tiny, you look at them through this telescope, and you measure the terminal velocity. And the terminal velocity gives you the mass of the drop. You can calculate the mass of the drop from there. Okay. And then what Mr. Milken did is he would shine X-rays on these things. The X-rays would ionize this air, and electrons would stick to the oil drop. Okay. And then electrons would stick, and he created an electric field, and the electric field would exert a force on the oil drop in that direction. So the electric force on this guy was E times the charge on the oil drop. And here was the weight of the oil drop. Remember, he found that measuring the terminal velocity. So now, by adjusting this electric field, he would suspend these oil drops. This is equal to that. So EQ equal to mg. He knows this, he knows this, he knows this. He can calculate that. Can I help you?
Oh, I just came to class.
Are you in the right room?
Yeah. Physics too, right?
I think so. What happened to your buddy?
Sophia?
Yeah.
She's not gonna be in class today.
She's
She's going to lab though, don't worry, she overslept.
All right. I'm going to up attendance grades. What do you think? 5 points are not working. All right, so you can calculate the charge. And he did this for thousands and thousands of drops. And what he found was that the charge on the drop is always an integer multiple times the minimum charge. And that we know today is the charge of the electron, okay, and the charge of the proton. And that fundamental charge is 1.6 times 10 to the minus 19 coulombs. I'll even let you sign this thing today. Well, you can do it later.
Can I sign Sophia's name or?
No. All right, so when you learn this kind of stuff, you can solve problems like this. So here's a factory, and look at this, it's spewing out this smoke. Okay. If you live anywhere close to this factory, you'll have chronic bronchitis. Real, for real. What's that?
I believe you.
So how do you fix this problem? You got to remove all of this. What's that?
Leave the area?
All right, so here's how you fix that. You see, these are metal plates, and you do the following. You give me a sheet of paper.
How does the carbon stick to the metal?
Oh, there's more to the story. Okay, so these are metal plates, and these are wires. You put these wires between the metal plates, and what you do is you connect maybe 100,000 volts to the wire and the metal plate. If the metal plates, the wire is at negative voltage. If you connect a high voltage, negative voltage to the wire, it'll spit out electrons. Good. So here are these smoke particles. The wire is spitting out electrons, and the electrons stick to the particles. The plate is positive, and now that the smoke particles are negatively charged, they'll go stick to the metal plates. So you remove all the smoke particles. And then every once in a while, you shake the metal plates and drop out the smoke particles. You can remove 99% of the particulate matter. So, and these guys are all happy. But you know, we had to pass legislation for that. Why?
Does it cost money to put that?
There you go, my friend. There you go. All right. So here's how the Xerox machine works. Yeah. There are some materials called photoconductive materials. Okay, so what does that mean? So if these materials are in the dark, they're insulators. If you shine light on them, they become conducting. So what was the difference between an insulator and a conductor?
Free charge.
Free charges. So what is happening? You shine light on them, free charges are becoming available. Light excites charges, and free charges are becoming available. All right, so selenium is such a material. Okay? So what you do is, here's a metal drum, take selenium, coat the metal drum with selenium, and then sprinkle it with positive charges. What you're doing is removing electrons. But anyway, so now selenium is charged, and it's on this, but selenium, remember, is insulating. And so these charges don't leak out to the metal drum. This is all in the dark. And when you want to make a photocopy of this, okay, so here's the dark, you shine light on it. Wherever light falls, selenium becomes conducting, and that charge leaks away to the metal drum. Wherever there was a dark spot, Selenium is insulating, and that charge doesn't leak away. And now you sprinkle this drum with a negative toner. So negatively charged toner, which will stick to this positive charge. And then take a hot piece of paper and roll it over the drum, and now you have a photocopy. Okay. In a laser printer, what your printer driver is doing is a laser is scanning, and what is the printer driver doing? It's turning on and off the laser at the right time. Okay? So that's how a laser printer works. Has anybody here seen an inkjet printer? Mm-hmm. Mm-hmm. All right. All right, let's talk about this. So, so what was the story? How does a positive charge influence another charge in New York City? See, this charge created an electric field all around it. And if you place another charge here, all that the charge is doing is feeling the charge right next to it, where it's located. It doesn't care how the field was produced. Okay? So this guy is just feeling the charge next to it. Now, in this simulation, what has happened is this guy is comparable to that charge, and he's producing his own electric field around. So this is the net electric field between the two. Okay? So when you put a sensor has to. Now here's another thing. So here's a very nice, beautiful, symmetric thing. What produces an electric field? What produces an electric field? A charged particle. A charged particle produces an electric field. What do you need to sense an electric field? Another charged particle. Okay, so whatever produces it is what you need. Masses produce gravitational fields, so you need another mass. Okay, too. So in this simulation, this charge is small enough where it's not disturbing the electric field produced by this guy. Okay. Okay, so this guy is producing an electric field all around him. This is called a dipole. Two equal and opposite charges are dipole. And here's how the electric field looks like around a dipole. Okay. In lab, we'll map this electric field exactly like that. Not today, but in a little bit.
What are we doing today?
Today, we'll measure the speed of sound. Okay, so this is a dipole. Dipole is two equal and opposite charges, and that's the field that is produced around it. Okay, so we said that this guy produces a field, and other charges just feel the field right next to them. Okay. So you already know the answer to that. Suppose one charge moves, how would the second charge know that the first charge has moved?
Field change.
Field change, yeah. Okay, so here are some of the rules for drawing field lines. Electric field lines start on positive charges and end on negative charge. This is just what we draw. You can, in an alternate world, or you can, in a parallel universe, you can have them start from the negative charge and end on the positive charge. It doesn't matter. So here's what we use. Number of lines leaving a positive charge or approaching a negative charge is proportional to the magnitude of the charge. So if the charge is twice as big, you draw, to indicate that, you just draw twice as many lines coming out. Electric field lines indicate the direction in which the positive charge would move. So what we are saying is, and let's make sense of this. So here is a positive charge. If I place another positive charge, which way would it move? So positive charges move in they feel a force in the direction of the electric field. And if I place a negative charge here, which way will it move? That way. So positive charges move in the direction of the electric field lines, and negative charges move in the opposite direction. Yeah. If you want to indicate a higher field, a stronger field, you just draw more lines. Okay? So the number of lines per unit area is greater. Okay? These are just little ways of indicating electric fields and their strengths and all that. Okay. The force felt by a charge in the presence of this electric field is that. So if the charge is positive, the force is in the same direction as the electric field. If the charge is negative, the force is in the opposite direction. So the electric field is the force felt by a charge divided by the charge. The electric field is force per unit charge. Okay. So the units of electric fields are, units for force are Newton, and this is Coulomb, Newton per Coulomb. Okay. So units for electric field are Newton per Coulomb. And about 4 chapters later, we'll also show you that units for another unit for electric fields are volt per meter. But we'll tell you about that in a few chapters. Okay, so units for electric field are either this or this. So here is an electric field. Positive charges move along field lines in the direction of field lines. Negative charges move in the opposite direction. Okay, so here's a positive charge and the field lines radiate outward. The magnitude of them will get smaller as you go further out. Okay, so here is the electric field. There's the Coulomb's constant, that's the charge, and that's the distance at which you're figuring out the electric field. This guy is a unit vector pointing radially outward. Okay? So that gives you the direction. From a negative charge, this guy is negative, and the electric field lines are pointing toward the charge. Okay. If you wanted to find the electric field at this point, due to several charges, you use the superposition principle. You find the electric field due to this guy at that point, electric field due to these guys, and add up all the vectors. Okay. An electric dipole is 2 charges, equal and opposite charges separated by a distance. Okay. And this is a very important thing. So life couldn't have evolved without this guy, but anyway. This is a dipole, 2 equal and opposite charges separated by a distance. The dipole moment is a vector pointing from the negative charge to the positive charge. It's denoted by P. Okay. And the magnitude of the dipole moment is one of the charges, the magnitude of one of the charges times the distance between the charges. Okay, so that's the dipole moment. And like I said, the water molecule, the Mickey Mouse molecule. Which guy is greedy for electrons? I'm sorry? Oxygen. And these guys have given up their electrons, so they're the positive charge, center of positive charge. Okay. For a methane molecule, there's the carbon, it's a pyramidal shaped molecule. Okay. For a methane molecule, the center of positive and negative charges are right on top of each other. For a nitrogen molecule, the center of positive and negative charges are right on top of each other. For an oxygen molecule, the center of positive and negative charges are right on top of each other. For any atom, the center of positive and negative charges are right on top of each other. So none of those guys have any dipole moments. There's 10 to the 28 molecules in this room, air molecules. What is the dipole moment of each of them? 0. Okay. This guy has a dipole moment. Very important. So here's the amazing thing. Absolutely amazing. Okay. What this is you can make molecules like this. Okay. So what is this molecule? Here's a molecule. The head, make it polar, and the tail is neutral. Okay? Well, what use is this? Okay, so let's do the following. Okay, so we're going to use that molecule. What we'll do is, we'll take a glass of water, okay, and throw a bunch of those molecules. In there, okay? Now I'm going to draw a big one. Okay, what happens? This this head will attach to the water molecule like that. Why?
It's attracted
Yeah, this is a low energy configuration. The positive charge is attracted to that. Okay? So, and this tail doesn't care about the water molecule. Okay, so this is a hydrophilic head. This is a hydrophobic tail. Okay, so you throw a bunch of these guys in there. And what ends up happening is the following. Water and water. So throw a bunch of them and they will automatically turn into a sphere, arrange themselves into a spherical shape. That'll be the low energy configuration. Why do you care about that? Now you have a chamber for life to evolve. Okay? All because of that dipole moment. All right, so here's a dipole. And what is the electric field far away? Far away, what do you see? This positive charge is sitting right on top of the negative charge, and you see a zero electric field. Okay? But if you're at a distance not large compared to this, then you'll see an electric field. And it turns out that the electric field falls off faster than for just a charge. Okay, so I'm not going to go through this detail. So this is giving you the magnitude of the electric field along an axial point. Okay, and you're measuring distances from the center of the dipole, that's Z, the electric field falls off as Z cube rather than R squared, than the distance squared. Okay, so it's falling off faster from a dipole. Right, so just keep that in mind. Okay. The electric field from a point charge at a distance is given by kq by r squared. And then there's a r hat. That's the unit vector pointing away from this. So if the charge is positive, the electric field is pointing away. And if the charge is negative, the electric field is pointing toward it. If you're super rich and you have a cloud of charges, how do you find the electric field due to this guy? You're calculus experts. What do? You break this cloud into point charges. Find the electric field due to this guy, there, due to this guy, there, due to this guy, there. But just add up all the vectors, and that's doing an integral. Adding things up is doing an integral. So here are vectors. That is the electric field due to this little piece of charge at that point, okay? And then for all these guys, all this will be different, but you just add them up. That's how in principle, you calculate the electric field due to this cloud of charge at that point. Okay, so if you have a thundercloud forming this afternoon, you can calculate the electric field in the parking lot by doing this integral. But of course, that integral is impossible to do. That integral you can do in very symmetric situations. Okay? So again, what you want to do is you want to calculate the electric field due to this distribution at that point, doing this integral, which is impossible to do, but in certain situations. Then, if you wanted to calculate the electric field at that point, you had to do another impossible integral. So we've given you an infinite series of impossible tasks to do. So there are some cases where you can do it, and so we'll prepare you for that. Okay. We define the charge density as the amount of charge per unit volume. Sometimes we spray walls with charges, so we define surface charge densities. Sometimes we spray wires with charges, so we define linear charge density denoted by lambda. Okay? So let's say you had a ring of charges, this integral that we talked about. Okay. So here's the ring of charges. You could break this up into little pieces and then do this integral as long as you're evaluating the electric field along these axial points. Then you can do this integral. Okay, I'm not going to show you how to do it, but you can do it along these points. If you want the integral, if you want the electric field there, good luck, you're on your own. Okay. Along those points, here's the answer. Okay. A is the radius of the ring, and x is the distance from there. If here's a disk that is uniformly charged, you can do that integral along these points. Okay. How about at this point? Good luck. Okay. So you can do it along these points. What is the electric field along those points? There is the electric field along those points. So somebody did that integral for you. Okay. Again, it's about doing that integral where the charge is, you've broken up these charges. This is the charge dq. So here's an absolutely amazing result. Okay. What is the strength of this electric field here at a distance r? Kq divided by r squared. Okay, so what this equation is telling you is the further out you are, if you're twice as far, the electric field strength is 1/4 as big. And so you go further and further. If you have a charge here and want to know the electric field at Pluto, that's almost zero. Okay, now we'll do the following. Here's a wall. Imagine this is an infinite wall, and you're going to spray it evenly with charges. How many charges are there? Infinite number of charges. And you're going to find the electric field at this point. You see, for this point charge, the field fell off as 1/r squared. For this guy, you're going to find the field here and here. So if you sprayed it with positive charge, the field will be in this direction. And here's the expression for the field. Sigma is the charge density, charge per unit area, 2 times epsilon naught. Epsilon naught is a constant called the permittivity of free space. Is there anything strange about this expression? Anything that jumps out at you besides the candy?
It's a protein more high.
What's that?
Protein more high.
Oh, I see, okay. Anything jump out at you?
It's finite.
It's finite.
They're even and opposite.
I'm sorry?
They're even and opposite.
There's no distance information. From the wall, the electric field here is the same as here, as here, as at the end of the universe. Amazing. Exactly.
Is it like the magnitude of charge is so great? It's an infinite.
Yeah, so each charge, the field due to each charge is decreasing, but there's an infinite number of charges. Okay? But, so, that's the amazing thing about this. Okay? Now, what produce... So I'm going to speed up. All right. What will produce an electric field? Charges produce electric field. Electric fields are measured, units are Newton per coulombs. And here are some electric fields. So in that fluorescent bulb, inside the bulb, the electric field is 10 Newton per coulomb. Outside in the atmosphere, it's about 100 Newton per coulomb. Anytime you see a spark in air, the electric field is 3 million Newton per coulomb, greater than 3 million Newton per coulomb. Okay. So we'll say critical electric field at this atmospheric pressure is 3 million Newton per coulomb, and we'll say it's, remember, we'll tell you that that's equal to volt per meter. Okay, so anytime the electric field is greater than that, what will end up happening is a spark in air. Okay, so let's figure out what is happening in lightning. Here's the thundercloud, here's the ground. And if the thundercloud gets charged, how does a thundercloud get charged? there's a lot of turbulence. Remember, when you walk across a carpeted floor, friction can separate charges. Just like that, water molecules in the turbulence, they separate charges. So let's say they create an electric field greater than 3 million volts per meter. Okay, normally air molecules are neutral and air is neutral. It's an insulator. Okay? And if you create an electric field, what happens if there is a stray electron, the electron moves in that direction. The electron will speed up. What will happen as the electron speeds up?
It's the magnetic field.
Eventually it'll hit one of the air molecules and then lose all its energy. Okay. If the electric field is less than 3 million volts per meter, the electron will hit this molecule and lose its energy and nothing happens. If the electric field is greater than that, it gets enough energy that when it collides this guy, it'll knock off electrons. These guys speed up, they'll knock off electrons. So soon as you reach that critical value, you're starting to knock off electrons from air molecules. You make this conductive. You make this a copper wire. And there's a discharge. So anytime you see a spark in air, the electric field has increased to greater than 3 million volt per meter, and the electrons accelerate and speed up and start knocking off electrons from air molecules and make it conductive. Where else do you see this phenomenon? Or you don't see it, but where else does it happen?
In the atmosphere.
In your spark plug. That's what's happening. In the spark plug, you're creating an electric field that's greater than 3 million volts per meter. You get a spark. What is the job of the spark? You light your air-fuel mixture. All right, so the force on a charge is charge times the electric field. Okay. We won't worry about that. So here's the famous dipole molecule. Okay. So this is the center of negative charge. There is the center of positive charge. Okay. So now let's do the following. So you have now I'm going to simplify this drawing. Okay. There's the center of positive charge, and this is P. Okay. Now what I'm going to do is I'm going to place this in an electric field. Okay, so here's an important application, very important application that you'll study. So what happens to this positive charge in the presence of this electric field? What is the effect of this electric field on this positive charge?
Moves away from the direction or towards?
Toward the direction, okay? So this guy feels a force in this direction. How about the negative charge? In the opposite direction. So here, let's say you have a dipole moment and you place it in this electric field. This guy feels a force like that, this guy feels a force like this. It turns towards the electric field.
Will it continuously spin?
It aligns, yes, so it'll spin, but okay, it aligns with the electric field. Then what do? You're mean, so what you do is you flip the electric field. Now, the proton, then what do? Flip it again. See, what have you done? What have you learned to do? You have learned to grab a dipole moment and jiggle it. That's what a microwave does. It grabs a water molecule, jiggles it. 5 billion times a second. What did it do? It added energy to the water molecule. And then that water molecule shares that energy with anything that's surrounding it. That's how you heat your food in the microwave. Yeah. So the torque on the dipole is P cross E. There's the magnitude of the torque. And of course, when you're changing it, if you let go, it has kinetic energy and it'll oscillate back and forth. Okay, so the potential energy is on the dipole in the presence of an electric field is given by minus P dot E. Okay. All right, so again, with the torque, what you can do is you can align the dipole, and then when you flip the electric field, it goes back. So you can jiggle the dipole moment. Yeah. All right, that finishes the concept.